Can I have the slides, please? Yep, I am sharing. Right there. So, thank you for coming. I am a data scientist here at WISE. Before we start, I want to address the convoluted title to avoid the word big data. Now you see that I decided to just go on and put it there, right? Because we try to avoid this word. It's not so nice. Sometimes it is nice to put on your CV, but what it really is big data, right? So today we have a talk on pipelines, data pipelines. And this is supposed to be something that caters a little bit to beginners. So I'll go very quickly through Airflow and what you should do and you should avoid in Airflow. And after that, I'll talk a little bit about Spark 2. Let's see how time goes. I have planned that we should have 30 minutes for a demo, maybe a little bit more. So a little bit about myself. Whoa, that was loud. 1 second. Better? Yep, okay. So I am a data scientist here in FinCrime, and I am a computer scientist by training. In my free time, I enjoy doing things like sailing, practicing jiu-jitsu, although nowadays I can hardly fit in my gi. Yes, I have gained a little bit of weight, but my girlfriend is on that, so losing that. And also playing CSGO, a little bit of a nerd, but yep. And coffee, making coffee, drinking coffee all the time. Maybe I have had a little bit too much today, so bear with me. Right, before we get into the demo itself, I'll talk a little, wow, the sound is really varying, right? Do you think it's best if I get the mic? Or is the volume okay? Yeah, because to me it's varying a lot, but okay, all right. Anyways, we'll talk a little bit about machine learning in FinCrime. Yeah, it is, all right. All right, so coming back. Talk a little bit about machine learning in FinCrime at WISE. Again, we have many squads and machine learning in most of them or all of them. I'll focus on the use case in FinCrime when we talk about fraud, anti-money laundering, scams, and other things. Talk a little bit about the motivation of this talk too. And then we go through the demo. In the demo, I'll talk a little bit about orchestration and computation. You can see here that I crossed out DBT. I was going to talk about it, but we're still playing with it, so I don't feel confident talking to people who might know much more than I do. And then we have the closing talk. Just before we start, let's see here. Do we have people here who work actively with Airflow? Can you raise your hand, please? People who work with data pipelines. Ooh, okay. Software engineers that know how to use Scala. Right. People looking for jobs. All right. So why are we here at WISE? WISE is a global company, technology, right? And we want. Oh, sorry. Coming back. Right. So we want to build a world where people can have money without borders, right? What does it mean? It means instant, convenient, transparent, and eventually free. WISE has launched in 2011, and since then we have been working hard to become operational and profitable. We have been profitable for 5 years now, and today we help over 13 million people transfer money across the world and businesses too. And monthly we have an average of 7 billion euros transacted in our platform. That means 1 billion euros saved in fees every year. Right. Now, where does FinCrime come in this? FinCrime has a direct impact in some of the pillars, right? So we have instant, convenient, transparent, and eventually free. How do we impact the part of instant? Risk assessments. Our risk assessments have to run fast so that we can have instant transfers. Right now, we are at a rate of 49% of transfers in our platform are already instant. What does instant mean? Well, 20 seconds, right? But that's our definition of instant because we're sending money across borders. Then convenient. How do we impact convenience? The precision that we have to detect fraud and non-fraud. Is the audio still okay? Yep, all right. So The precision at which we can detect fraud and non-fraud directly impacts on the user experience of our customers, right? You do not want to be blocked or have your money blocked when you're just a good customer that has a long history with us. And eventually free. Right. Our ability to detect fraud, scams, our ability to comply with regulators, to comply with anti-money laundering regulations, all of these impact our bottom line product cost for our customers. Now, you may say that, hey, the solution to solve all your problems since you're scaling is just hire more people, right? And well, that is the case, one possible solution, but then we would never get to eventually free. That's our objective. So in order to be eventually free, we have to find another way. And luckily, we have seen in FinCrime and other squads too, that machine learning can help us achieve some of the benefits and maybe even scale more without raising the costs. It means more scalability, less complexity when managing static rules, discovery of different behaviors that humans cannot see, and evolution of new trends in our data. What is machine learning? Very brief, machine learning means features, models, and labels, right? Features are data points that you can use to capture a given behavior. Models are, people have very convoluted explanations of they are, but simplifying, models are software that can learn rules. So instead of doing a bunch of if and else in your code, you give the model data, features, that capture a given behavior, and let it give back to you rules. That's the idea. And labels are decisions from humans that help a model assess whether their rules, the rules that they created, are good or not. Right, models need data. How do we get data? We have production systems, right? And these production systems, they compute features real time. From there, we can get data to databases, and we have our analytics platform replicate this data to Snowflake. Right now, we use Snowflake. Are you aware of it? It's somewhat of a big company, right? So yes, we do use them very, very often. And after that, we get to the part of this talk, which is extracting data from Snowflake, the pipelines, right? What do we use in our pipelines? Well, this slide's misplaced. Sorry about that. I was going to say that all problems are solved, right? Nobody needs to worry anymore. We can just go home because everything is beautiful. Yeah, we have things that we need to improve. So what did we need to improve? Airflow is the orchestration tool that we have. This tool is, well, we love to hate Airflow, but the problem is not with the tool, is with the way you use it, right? So lack of modularization caused us a very, very hard time, caused us to have a very hard time testing code. It was very hard for us to test, and that caused a bunch of one-line pull requests. Who doesn't love it, right? In the end, you can just say, hey, look, I had 2,000 PRs in 2 months. Wow, you must be a genius, right? Yeah, not so much. Spark, we lack optimization of some of our scripts. That means slow compute and a lot of out-of-memory issues. And the queries, we still have some problem with that. We have been working actively on lack of incremental logic, right? What happens is that you go to your data grip, Snowflake, you create a query there, you limit by 5, and after that you just take the 5 out and put it in some pipeline. Now expect it to run, right? It doesn't, well, sometimes it does run, but you see that it takes a very long time to do it. How was the pipeline before? Well, you can see here in the picture that we have a bunch of reds, a bunch of yellows, some things that never actually ran, and our computation time was in around 6 hours and a half every day in the morning. That was the time that it took for us to extract data. It is a lot of data, okay? You can ask questions, I'll talk a little bit about it, but right now we're somewhere around 700 gigs for one of our datasets. So how much data is big data?
Do you want questions as you present, or do you want people to batch their questions towards the end of this slide?
Let's do it now.
Yep. Okay, thank you. So yeah, whoever has questions, then feel free to raise your hand. Thanks.
All right, no questions about big data. Nice. All right. So yes, we do have big data. If nobody complains, let's call it. How is the pipeline now? 1.5 hours to compute, 1 hour and a half. So from 6 hours and a half to less than 1 hour and 30 minutes every day. Is this perfect? No, we still have a lot of opportunity for improvements, and we'll talk a little bit about this after the demo, but it's already much better, much more reliable. You can say that there is some pink there. The pink was a date that we paused the pipeline, and then when we re-enable it, we didn't have to compute these things because now we do incremental processing. So look, we don't need to do it anymore. How does extraction work? Well, like I mentioned, we have Airflow, Spark, and this technology that some people are aware, it's called Delta from Databricks. Have you ever heard of it? It's actually open source. Just one person. Nice. Data engineer? Yeah? All right, let's talk afterwards. Anyways, so Airflow to trigger jobs, and then Spark to compute, and Delta to version data. All of these tools can do much more than that, but that's the baseline use that we have for the new pipeline. Demo. Before we go to the demo, do you have any questions? I have a hard time figuring out how I'm going to do the demo and hold the mic, but let's see. So let me open up here. Okay. Let's actually run Airflow. All right, it's starting. So, wait. Right, this is the EU. Unable to connect. Technical problems. 1 second. Okay, Airflow is ready for us to open it. Let's go back. Open the UI. Ooh, okay, that was unexpected. Just 1 second. Yes, this is not a production system. I didn't do this, Airflow does this, right? But that's just development. So yes, don't shoot the messenger. Oh, wow. Okay. So we're going to have a live session of debugging passwords instead. Yes, let's go with admin. Let's go. Right. Nobody even remembers it. It's not being recorded, right? Okay, this is not that good because we have examples here. So right there, when you start Airflow, now this has become a little Airflow tutorial, right? So you come here, you go to examples, and you take the examples out. Oh yes, they are out. So let's go back to the terminal. Let's see what's up. Let me open a different one. Let me define. Good thing we have a bunch of IT support here, right? Yeah. Remember, I'm just a data scientist. You guys are the engineers in IT. Password. Yep. It's not the correct one. Oh, right. Go figure. Anyways, so you can see that I already have a DAG here. A DAG is basically a pipeline. I'm not going to get too much into the details. So we have the first example. You can see that I have already run something here. I didn't want to run this live because it takes a long time to compute. If you look at it, 21 minutes, right? But let's look at the code, what this first one is doing, because this is the most traditional way that people start creating pipelines. You have Snowflake, right? Snowflake can do all the processing for you. So you go to your code and then you do all your imports, right? The most important here is Snowflake Operator. You're going to create a little DAG for yourself, which you can just say that is the same thing as a pipeline. Right here in your pipeline definition, you're going to create a task. Your task is a Snowflake Operator task. It's a query, right? So who here is familiar with queries? Do you work with queries every day? A couple of people? Yeah, nice. Yep. All right. So this is a simple query. It inserts data into a new table, creates or replaces the table, and inserts data, right? You can see here that I use some what's called templates to hide data that you shouldn't see, right? Information that you shouldn't see about our databases. And then here you have some control for date. This is information that you get from the pipeline. So you can actually access these macros so that you can control the operation of your pipeline. This is a terrible, terrible DAG. This is a terrible, terrible query because it's computing the same thing over and over again. The only difference between one day and the next day is the new data, but you don't care about that. You recompute everything, right? What is this doing? Can anybody tell me? It's selecting the user ID and the max transfer date. That's it. As simple as that, right? And you can see that it takes 21 minutes to run. So we must have a lot of data behind it. And if you go to Snowflake, which I won't do because we have a lot of sensitive information, but we have huge machines and we're paying a huge amount of money to run dumb things like this. And when we first looked at the pipeline, we realized that there were a bunch of this kind of queries happening every day. Remember, 6 hours and a half to compute. So how can we improve this? Suggestions? What do you mean by that? So think about this computation, max date, right? So every day we have new transfers and we have batch processing. So we have the replication happening overnight to Snowflake, right? The difference between one day and the other day totally depends on the date. So if you have a query that depends on date, you're doing it wrong if you're recomputing everything every day for this kind of computation, right? Because you know that yesterday the max date is yesterday, maximum. Some users don't transact, so then you have stale dates. But the maximum date that you can have is yesterday. Now that you are running the new day, the maximum date that you can have is today. So why not break this operation into incremental computation? Let's do that. So I have my AI assistant writing code for me here. As you can see, it's there, right? It's a little bit more complicated, isn't it? Because now instead of having just an insert operation, you have a merge operation, right? And this merge operation looks at your table that you have already created and the new chunk of data that is coming in. Where do you define this chunk of data? Between yesterday, so you add the date -1, and today. As simple as that. Now you have a query that is going to run in seconds, hopefully. So let's exit here. Not going to go into much more detail than this in Airflow, right? I'm going to jump the next part to testing. So decoupling the two things, computation and orchestration. But let's just see if this runs. Damn, didn't even have time to show it actually getting queued and running. It has already done, right? So it's already done. Let's clear it, come here again, say now pretend that it didn't run. Let's run again. So highlight green means that it is active. It's going to go to authentication. And then we come back here. It's going to show that it is actually running. If we go to the Snowflake UI, you would see the query submitted there and in the stage running. And hopefully it's not queued in the database, because that's what can happen when you have a bunch of people using the same warehouse. Let me take a look. Yeah, so it's done. How long did it take? Let's see. 44 seconds. It's okay, right? Compared to 21 minutes. So right there, simple little trick that you can do, just changing the way that you think about your data, you can now get a bunch of boost in performance, right? Reduce a lot of your computation and the expenditure that you have too. Right, let's go to the next topic. Any questions here? That's a beautiful question. We're going to talk about this right now. Yeah. So think about it. In this operator here, can you actually test this? You cannot, right? And unfortunately, or maybe fortunately, but when you go to Airflow providers, you have companies that create code and attach it to Airflow, right? And when you go to their documentation, you will see that the way they suggest you use their tool is not very modular at all, to be honest. This is the way that they want you to use it, right? You call the operator, and then you run the query right here from orchestration. So there is no space for you to test your code. How can we solve this? Decoupling, right? You have this clear concept of orchestration and the concept of computation. So why should you be mixing the two things and then you run into problems like this? Testing. How do you actually test your code if you cannot run it locally, for instance, before you even do a commit? To solve that, we have to break things apart. So let's create here a new file. Let's call it decoupled. How am I in time?
You have like 20 minutes.
All right. So we have decoupled, right? Now let me get my assistant to show me code here. Oh, okay. I just quit by accident. 1 second. Oh no, wait a second. This one is... right there. All right, so a little bit of silence, time to meditate, think about your questions, and now let's go to the decoupled part of things. Because this seems to be a little bit boring to people, I'm just going to skip some parts and go directly to the more interesting part, right? So let's talk about downsampling. Downsampling is a very expensive kind of computation that we use to reduce our training sets for models, because you can imagine that fraud happens very rarely, but when it happens, it has a huge impact. So you actually want to have datasets that capture your fraud, but if you just give it the data that you have, it's not going to, the model won't see it. So you actually have to take out some of the good customers from your training data and keep all of your fraudsters. Do you get the idea? So reduce the data, but don't throw away any of the fraudsters. You want to see all of them there. This computation is called undersampling or downsampling. It's expensive. Here is the orchestration side of things. So you can see that it's a simple Python operator, and I have a Python callable. It's a function. The first one runs with Spark. The second one runs with pandas, right? So let's look now into the actual function. And this function is the kind of thing that you can actually test. So let's open computation. Let's come here to source, downsampling. Right, what is it? It's a function that takes a path to your dataset somewhere, the name of a column, how many rows you want in your output data, and random seed if you want to provide any. You have some operations in the middle. This is Spark code, and you have the same thing happening down here with pandas code. Now this can be tested, right? How would you go about testing this? Well, you can use PyTest, for instance. If you code with Python, that's the thing that you choose to use. I did not develop any tests for this one, so let's go for the simple one. Get user mean transferred value, right? So you only take connection params, start date, and end date. You run a query, and from that query, you do some sort of aggregation on chunks of data, because we know that pandas cannot handle the big data sets that we have. So we have to break into chunks and run the computation in the chunks. In the end, we create a little aggregated data set, and we write this to disk. What about the test? Oh, yeah, I actually did write the downsampling test. Anyways. So, get user mean value right there. We have now the test that we can run with PyTest. I have here some fixtures that I can use for my authentication with the browser, right? As you have seen, whenever you run this, your browser is going to go to Snowflake, do authentication, come back and authorize your query. All of these here, of course, are in my environment, so that I can't share this kind of information, right? But the idea is that you get the parameters. So right here, the start date, end date for the query. We have the user ID, and I have pre-computed these values, right? I know that this is the value that should be returned. So this, in this case, is the average invoice value for a given day. In this case, between the 1st and the 2nd of July. Should we try to run this? What good is test if they can run? Right, so, Okay, that's good news. Right, I actually have to go into the pipeline, computation, tests, decoupled functions. What's up with it? Test decoupled functions. Pipeline, computation, test, decoupled functions. Get user mean transfer value. Test, get user mean. All right, anybody has suggestions? Now I'm baffled. Okay. I know what's up. I am in the incorrect directory. So let's give it a try again. When the environment is active, yes. All right, so the authentication is happening here in my lower screen. And let me see if the query is running. Yes, the first one ran successfully, as you can see. Now the second one is authenticating. And the two tests passed. So you can actually test now your code without having to submit things to your actual production pipelines, right? So Airflow. This is very useful because sometimes you cannot have access to all the setup that you have in production, but you can mock it, right? So that's the whole idea of having local tests. And right now we're working actually in mocking calls to Snowflake. So we don't want to have our tests actually going to the database and making it busy, right, with dummy requests. So what we're going to do is that we're actually doing mocking it so that the calls go to this local database and just pretend that it's actually a Snowflake call. Did I answer your question, sir? He doesn't even remember that he asked the question. He's pondering the meaning of life right now. Did I answer the question? Yes. Did you get a test? Does it work? Should we look into the code actually? Because right, we didn't see what's happening. So let's go back here. We can look into the code. I'm not an engineer, but I pretend to be. So what do we have to look here? We have to look into the import, right? So this is the import that we're doing. It comes from pipeline computation source, decoupled functions, and then the function that we're actually testing. If we go to the code of it, again, this is going to be inside computation, source, decoupled functions, and this is the function. What is it doing? It has a query. It is going to use pandas to read or to execute this query against a connection. What is this connection? Snowflake, right? So you have a Snowflake connection that you pass as a parameter. So right here, connection, actually not even the connection itself, the parameters. And then we have this auxiliary function that we create here, which you can see it's very simple, right? It's just Snowflake from the Python package and connect. You give it the parameters and now it goes to Snowflake and runs. Gives you back the chunks, you operate on top of the chunks. Here we're grouping by user ID, getting the invoice value and the transfer count, because afterwards we want to calculate the average value in this line right here for each user. The data is already grouped beforehand. And afterwards we write as a Parquet data type here to this data folder. So you can see user mean transfer value is right here, partitioned by date. So we actually have it run twice. We have 2 days here. Does that make sense? I'll consider silence okay. All right. So from here, we already have the big lesson that we learned and we're refactoring our pipelines. It is that you should not use tutorials as they come, right? You should always be critical of how the information is given to you. You should take a step back and say, hey, do I really want to use it this way? Because Snowflake will tell you, hey, just use my Snowflake operator. It's beautiful. Don't mind vendor locking, right? Don't mind these things. I'll just hike the prices next month and then, well, we'll talk about it. Whoa, you have to refactor all your code now because your whole code base depends on the Snowflake operator. Too bad, so sad, right? So we're actually trying to decouple the best we can from this kind of vendor locking. There are some vendors that are more difficult, right? For instance, AWS, but we're trying our best. All right, so I want to talk a little bit about Spark. I don't know if that interests you. I hope it does, but let's see the time.
Some time, like
Yep.
10 minutes, yeah, I guess.
All right, so let's get to Spark. Okay, right here, decoupled. Let's go to Airflow and see what's happening here. Right, now we have the coupled DAG example, and it has run. It ran only the first one, which is the one that we have just seen, right? Is the pandas get mean user transfer value. Now, what about the next computations? The next one is actually with Spark, and I'm not sure why it's not running. No problem. I don't mind losing the information, so I'm going to delete here. And let's try to recreate it. Let me see what's happening in Airflow. Okay, it is still running. Right, so the DAG is created. We're going to ask it to run. The first one is the one that we have already seen. So as I mentioned, it goes to authenticate to Snowflake with the browser using my personal credentials. It's going to run for a couple of seconds, and then the second one is going to start. Yes, right, this is the one that we care about. Now it's using Spark. If we come here to the terminal, you're going to see that it's creating a Spark session, right? These here are all the dependencies of Spark. So are you going to do this in your production Airflow? No, you're not. You're going to submit this to a cluster, right? But for the sake of example, I'm running in the same machine. Ideally, what you're going to have is you have a cluster, and you can use the Spark operator, or you can use something like EMR operator to submit your job to a cluster. So it's going to run. If we go back to the UI, we can see that it is still running. This one should take a couple of minutes. So while we wait for it, let's talk a little bit about Spark, right? What are the two main points of failure or problems with Spark? Can anybody tell me? There are two headaches, two things that if you get right, you won't have to worry too much about the hard documentation and all the different parts that you have to, the moving parts. What is Spark for? I heard the word distributed computing, right? What is that? That's parallelism. We want to parallelize computation, right? So if you want to make things run parallel, you have this concept of a map reduce. And Spark, the only thing that it does is brings the map reduce to the memory. So now if you have a bunch of memory, you can just keep your data in your memory and map computations to your data. That's beautiful, right? But it comes with a heavy cost, and you'll see very quickly that Spark is not magic, right? If you run on small data, it will never run out of memory. But if you have large amounts of data, you will have out-of-memory problems all the time, every time. So how do you avoid them? You avoid them with parallelism, right? Increasing the different amount of executors that execute at the same time. So if you look at this log right here, let me give a description first. This is a summary of your task, right? And you have the duration, garbage collection time, spill to memory, spill to disk, output size that is written, and the shuffle read size. So this is to give you an idea of size of your task, right? Each task is mapping a computation to a piece of data. What's the problem with this? Is this a good execution? Regardless of what's computing, would you like your process to take 1.6 hours? One task. Number 11. Out of 256. Would you like that to happen in your pipeline? Of course not, right? This is terrible. You're not using enough smaller tasks. So what you can see from this log already is that you need to increase your shuffle partitions and how many tasks you have running at once. It's much better for you to have smaller tasks that can finish quicker and more of them than having something like this, that you're having most of the time idle cores, right? Your CPUs are just idle waiting. That's a very good question, right? They shouldn't be synchronized, but because we did such a terrible job, this was on purpose, right? Let's be nice. Since we did this write operation at the end of this, and we wrote it to one partition only, so I did a coalesce, right? You have all these different executors, you force all of them to write to the same file. So now you have an I/O operation that is having deadlocks between the, not deadlocks, but concurrency between the executors. So you force all of them to finish at the same time, right? This is terrible. This is a very, very good comment, actually. Do you guys know Parquet file type, or are you still using CSV? Jesus Christ, do not do that, right? Let's kill CSV. CSV is nice if you have 1,000 rows, 10,000, 100,000. More than that, please drop it. It's not nice. Parquet is much better. You can have a whole talk about Parquet. The basic benefits that you get is you can have metadata associated to columns. You can do filtering before loading data to memory. So, back here, what would be a better scenario? This scenario. What do you think of this scenario? Now we have different percentiles, right? We have the smallest task running in less than a second, and the biggest task running 16 seconds. Is that good? Is that something that you want? Remember, if this is running in a cluster, you're having to send data across the cluster, network operations. So you have network operation to take 0.2 seconds for computation. That's garbage. That's terrible, right? You shouldn't run in a cluster. If that's the kind of results that you're getting, you should just buy a bigger machine and run everything in one machine with pandas. So this is also a sign of a terribly distributed operation. You have small tasks, too many small tasks. This could be perhaps just, we have here 80 executors. Instead of 80, you could have just 10, 5. You would have much, much better performance because most of the time is actually spent in network I/O, not in computation, right? Which is what you're paying for. You're paying for cores. That's the most expensive thing, right? So that's what you want to avoid.
Well, you also pay for networking, and especially if you're using AWS and you have your cluster distributed across different availability zones, then you pay twice on the way out and then also on the receiving end.
Fair point. Yes. So don't do that. So what is the halfway between, right? Something that you look at and you say, all right, this task is good enough for us not to have to optimize the shuffle partitions and the parallelism anymore, right? You have some tasks that run very, very fast. It's somewhat not even justifiable to have the network overhead, but then you have tasks that are running in around 5 minutes. So you see that 75% of your tasks take at least 50 seconds. That's good. That's something that you can accept, right? 50 seconds, 1 minute, 2 minutes is your target when you're talking about computation in a cluster. Depending on the task, right? Some tasks you can wait a little bit longer, but ideally you want to stay in this range of a couple of minutes, 4 or 5 maximum. More than that, you can just know that you could have more executors running at the same time and get things ready faster. So, what is the takeaway from the first point? Play with your two configurations that you have, shuffle partition and parallelism, right? These two are your best friends. Always give more and then optimize to less than trying to give less, running out of memory and never knowing what's happening with your job. Are we out of time? Yep. All right, so just to finish up, if we come back here, you can see that the Spark job actually ran, and oh, look at this, perfect. The Pandas job was never even able to run. It ran out of memory, right? Because you have bigger data sets and it cannot run. While the Spark job took 2 minutes to run. This one, the Pandas, took 4 to fail. So how much data is big data? Bigger than your memory, right? Should you use Spark? No, don't use Spark if you don't have to. If you can have more memory, use the memory and use Pandas. It's much easier, much faster. But if you do have to go for distributed tools, Spark is a very good option. Just one final thing. As you can see, I am a data scientist. I'm not an engineer, but we are looking for engineers. So I'm going to jump ahead of these slides and come down right here. ThinkCrime, machine learning and data engineering. We're creating this team inside of ThinkCrime to take care of our data pipelines, not only offline, but also online, which are the most important ones, right? We want to have risk assessments that enable instant transactions, not in 20 seconds, but in 1 second. So if you are an engineer looking for a new challenge, please come talk to me. 3 pillars are enable data scientists to do experiments. Please let me play with machine learning. I don't want to be doing the pipelines. Second one is to build pipelines that scale and that are fast, and to improve governance, right? Because we do have to handle regulators, auditors. We have to have transparency even for ourselves. So 3 pillars, come talk to me. This is my email and LinkedIn. Thank you very much.
Thank you, Otto. This was a great one. So before we go on a short break, does anyone have any questions? Let's start from over there.
So that's a very good question, actually. In our use case, we only use supervised models. So humans are teaching the models what is right and what's wrong. You do see many different cases where people use deep learning and unsupervised machine learning. It's not our case because we have to be able to explain the decision, and we actually have to be able to explain what feature contributed to a positive score or a negative score, be it fraud, scam, or anything like that. So we do have these tools for our operationals to keep check on the models. So when a model make a decision, he sees why the decision was made, what was the model version, and he has direct contact with us to go and get feedback, change, replace the model. So the question is about vendor locking, how much we could save by breaking these locks, right? This is a very good question because we are not only inside FinCrime using Snowflake, and we do have the cost centers, right? So we are one of the biggest users, especially in fraud, but to be honest, I'm not sure how much I can share about this information. I can just tell you that it's a lot, right? If instead of using Snowflake, we use, for instance, EMR, we can reduce the cost by a lot. Folds, right? Multipliers.
Thank you. And here was another one as well. Otto, if you can as well.
I'll repeat the question, yes.
Thanks.
The human annotates decisions of models if they're right or wrong, and we use that to loop back and feedback into model training. So the better labels we have, the better models we have. So this is discrimination, you mean in the sense? Yeah. So we have analysis on top of model performance, right? And also on top of our operationals performance. So we do see every now and then that there is mistake in labeling. So we have to go back to it, change the training data. So we update the labels, right? We call these batch operations that happen every now and then. But I think that the biggest point here is to strive for excellence in our operationals, right? So we try to give them enough time and training and constant training, feedback, time to talk to other operationals too, good leadership so that they can make the least amount of mistakes that is possible. But there is still always a little bit of mistake included. This is a benefit that we have of having so much data, is that these mistakes, if we have enough good labels, they are just noise into the model training. So it's not that they are going to teach incorrectly the model, they just make it harder for the model to learn the correct signal. So they impair the learning, but they don't teach wrong things.
Thank you. Any more questions?
I think the machine learning part was more interesting, right? Maybe should have been about machine learning.
Maybe definitely next time. So this let's make it the last one, please.
Yeah. So that's a very good question. It is, how do you validate that the decisions of operationals are truly correct, right? When you call something fraud, that it's actually fraud. In an ideal world, we would have the police working closely with us in order to take criminals to justice and then make a decision. A judge makes a decision, right? Because we are not judging anything. We're talking about people using our platform. So whenever we call something fraud, we're saying that this has either caused loss to the company and we're not willing to have this kind of behavior in the platform, right? Or other cases, for instance, of regulators, AML. We have regulators that ask to see cases, right? They come and say, hey, let me see your data, let me see what was your model prediction. So we are trying to abide by rules, law, and regulators while impacting our customers the least possible. We want everybody to use the platform as long as they're using it correctly. How we judge correctly is why we have operationals, right? They are well trained, they interact a lot with the police. Like I said, ideally we would have a trial, but we do have interaction with the police, and that's, you cannot let the perfect be the enemy of good, right? So we are happy with the quality of output that we have had so far.
Thank you, Otto. It was a great talk. Please, may I ask for a round of applause for Otto once again.
Thank you very much.
And from
engineers, come talk to me. I'm serious.
And then from DevClub side, a gesture of appreciation. Here, a branded socks for you.
Thank you very much.
Yeah. Thank you so much. And ladies and gentlemen, we will have a